Welcome. In today's lecture, we will cover Part 2 of Chapter 1, Chemistry, a Science for All Seasons. In Part 1, we built an introduction to what science and chemistry are, and began to discuss what a scientific theory and scientific law are. Often, the phenomena that we're looking at, or the theories that we're looking at, are extremely complicated processes. And in this case, we can use models to describe or pictures to represent invisible processes. For example, we can model the process of evaporation or the process of water being at the surface of a beaker using a model. And so, for example, in A, on the left, when a container is standing open to the air, the water slowly disappears. And over time, that'll lead to the second, on the right here, the second picture, where we have the water level being lower, meaning more of the water molecules have mixed into the air with the nitrogen and oxygen in the air. So with our visible eye, we can't actually see the water going from the liquid phase to the gas phase, but with the blowed up portions in the circles, you could see that the movement of those molecules is modeled. So this would normally be a process that's invisible to the eye, but using a diagram and model, we can make it more tangible. One of the most common types of modeling is the modeling of molecules. Molecules are extremely small, and molecules are also groups of two or more atoms that are held together by chemical bonds. A molecular model is a three-dimensional representation of these molecules. Without the most powerful microscopes in the world, it's actually impossible for us to see these with the naked eye. But we can model them using structural elements. So for example, what are some of these molecules that you might be aware of? If you've ever seen the popular TV show Hot Ones, where they test different hot sauces, you'll notice an experience that the contestants have where they are tasting really spicy molecules, really spicy peppers, and so this is the molecule that's responsible for their reactions. This is capsaicin, and when you eat capsaicin, you'll experience the effects of really spicy food. Another common molecule, especially one that you might be familiar with as you stay up late studying, would be the active component in coffee. So here's the structure of the active component of coffee, which is caffeine. And you can see this model illustrates, for example, there's an oxygen, and it's bonded to this atom here, which is a carbon. The ones that aren't drawn in are called carbon, and then that's bonded to a nitrogen. So this is a model of all the different atoms bonded together. And then finally, in the bottom left, we have some oranges, which are one of the primary components contained is ascorbic acid or vitamin C, and so this is the molecular structure of vitamin C. Science is limited to studying that which is observable, so we have to be able to detect or measure what we're looking at. And it's all as well as natural processes in which variables can be controlled. We must be able to change only one variable at a time in a series of experiments and keep all of the other variables constant. Science and technology are directly interrelated, and they both involve risks and benefits. And so for us to decide if a certain technology or science is worth utilizing, we have something called a desirability coefficient. And this is the benefits divided by the risk. One of the goals of science is to solve some of the problems that society faces. And so there's a lot of money both in private industry and in academia, as well as government funded monies that are put towards scientific research. And so there's two types of scientific research. The first is applied research. Applied research involves studying a specific problem in the industry or the environment. And so an example of this would be George Washington Carver's research. He studied peanuts, and in the process of discovering these peanuts, in the process of researching these peanuts, he's able to develop more than 300 different products from the peanuts. The other sector of research is called basic research. In basic research, there's a search for the knowledge to increase the general understanding. And a lot of the times the basic research, the findings from the basic research are then taken later on and used to, they're applied to solve a specific problem or question. For example, Gertrude Ellion's work with purines and their role in cells is an example of basic research. He discovered more about these compounds and how they worked within the cells, and then this research can then be later used for more involved research and as potential therapies. In this figure, we're looking at the risk of death from a variety of different actions. So this is in the United States. All causes, so 25% of deaths in the United States are caused by cigarettes, 20% are caused by heart disease, 14% are caused by cancer, 1% by motor vehicles, etc. Sometimes the risk of an action is different than the perceived risk. For example, if we look at airplane accidents, that's a very small number relative to motor vehicle accidents. But then we also have a piece of data that's not necessarily easy to interpret right away. For example, we have a much higher chance of dying in a motor vehicle accident, but how many hours a year is somebody driving in a car compared to flying in an airplane? So this data could potentially be a little bit misleading. Here's another example. In Florida, at University of Tampa in Florida, there's often a lot of conversations about staying away from fresh water because we have alligators in all of the lakes and ponds in Florida. Well, what do you think the chance of being eaten by an alligator is as a risk of death in the United States? The chance of being eaten by an alligator is actually 1 in 3.2 million. There are very few alligator deaths a year. It's even less common than being in a terrorist attack or an airplane accident or anything like this. It's way even more rare, but it's something that a lot of Floridians fear. So let's move on to matter. Chemistry is the study of matter and its changes. Matter is anything that has a mass and also a volume. This leads me to a little joke. Why can you never trust an atom? It's because they make up everything. We have two different units that we can use to describe a substance. We have mass and weight, and these two units are fundamentally different from each other. Mass is the amount is the measure of the amount of matter in an object. When we have a mass of an object, it's not going to change if it's on the moon versus if it's on Earth. It's going to always have the same mass. This is different than weight, which is the measure of the gravitational force on the matter of an object. So this is the mass times acceleration. The acceleration is the acceleration due to gravity. So the weight of an object is going to be different on the moon versus in space versus on Earth. If there's zero gravity, then the acceleration is zero, so it would have no weight. But that object would still have the same mass. One thing that chemists can do is use their knowledge of chemistry to change matter and turn it into more useful substances. When we're distinguishing different types of matter, there's two types of properties that we can look at. We can look at the physical properties of the matter and the chemical properties of the matter. The physical properties of the matter are those properties that can be observed without changing the substance. These characteristics include things like color, odor, mass, weight, density, boiling point, and melting point. We can observe something like the color by looking at it. We can observe something like the weight or mass, depending on where it's at, by weighing it. These properties won't change at all while we observe them. Here's a table of some examples of physical properties. For example, a temperature is a physical property. A mass is a physical property. The structure, if it's crystalline versus it's amorphous, or the color, if it's yellow or brown. So the most important part for the physical properties is we can observe these properties and we can do it without needing to change the substance at all. If we want to observe a chemical property, we're going to need to change the substance in some way, shape, or form. So for example, iron has the ability to rust. This would be a chemical property because the composition of the iron would change. The iron undergoes a chemical reaction with oxygen to form iron oxide. So a chemical property is the property of a substance that could only be studied by forming brand new substances. This leads us to physical changes. Physical changes can occur when the substance is not changed, but the state of the substance is changed. So some common examples of states are melting, boiling, freezing, and sublimation. These are state changes. So when water goes from ice to liquid, or if we are boiling some pasta, for example, boiling some water to make pasta, and the water slowly decreases in volume over time, that's boiling. The water turns from water to gas phase. These are examples of state changes. And these would be examples of physical changes. So some key points of physical changes. They only can change the appearance of a substance, but the chemical composition does not change at all. When we boil water, the chemical formula of water is H2O as a liquid, and it remains as H2O when it turns into a gas. The chemical change of a substance will cause an entirely new substance with a different chemical formula to occur. So this would be a chemical change. Chemical changes are also known as chemical reactions. When we turn one chemical into another chemical, that's a chemical reaction. The starting chemical would be the reactant, and then the reactant will turn into a new chemical, which would be called the product. That's the end result of a chemical reaction. So a chemical change is a process that causes a substance to change into a new substance with a new chemical formula, and a chemical reaction is a process involving the breaking or making of interatomic bonds between the atoms. Going back to the Lego analogy, if we have Lego pieces and they're all connected together, right? We can make a new structure by removing one of the pieces and then replacing it with a different piece. This is similar to what happens in chemistry with atoms, where the different atoms are bonded to each other, they're joined together, and then we can break the bonds and form new bonds in the form of chemical reactions. And then finally, a physical change is a process that does not cause a substance to become fundamentally a different substance. So the chemical formula of the substance is exactly the same. So we can classify matter into three main categories: solid, liquid, and gas. A solid is going to have a definite shape and a definite volume. This would be something like ice. A liquid is going to have a definite volume but no definite shape. So the liquid will take on the shape of whatever container it's in. A gas is much more random. It has neither a definite volume nor a definite shape, and it will continue to expand if it's allowed to, if it's not captured within a vessel. If we look at the states of the matter, we can see that solid, the molecules are going to be much more close together. In a liquid, the molecules will be further spread apart and can take on whatever shape that they're placed in. And then finally, gas, the molecules have the largest volume of the three. All matter can be classified into the following subsections. First, we have substances and mixtures. A substance is a molecule that's going to be a pure form of matter. And this substance is going to have a fixed composition and that doesn't vary from one sample to another. So it's going to be a pure form of one single type of molecule. We can then break a substance down further into two subcategories. An element is going to be a pure substance of one single type of atom, one single element. This is the fundamental form from which all materials are constructed. A compound is going to be multiple elements combined together. It's a substance that's made up of two or more elements chemically combined in a fixed ratio. In a mixture, we're going to have multiple substances combined together. If we have these multiple substances combined together in a way that's completely uniformed, we have a homogeneous mixture. This would be something like a bronze alloy. If we have a heterogeneous mixture, we're going to have a variety of different elements or compounds combined together randomly. And so something like picking up a handful of sand would be an example of heterogeneous mixture. All matter can also be classified into one of these four ways. These are the different states of matter. We can have gas, solid, liquid, and plasma. For the scope of this course, let's focus on just gas, solid, and liquid. Now, there are also 6 other vocabulary terms here. These are the transitions between the different states of matter. So, for example, if we want to go from a liquid to a solid, that's freezing. If we want to go from a solid to a liquid, that's called melting. We can go from a solid to a liquid, and then we can go from a liquid to a gas. That's vaporization and condensation. And in some examples, we can even go directly from a gas to a solid and backwards. That's sublimation and deposition. Take a moment here to look at the 4 following examples of changes. These changes are either physical changes or chemical changes. You can go ahead and pause the video and try to decide for yourself which type of change each of these examples are. If you chew on an ice cube, what type of change is this? the ice in the ice cube is going to melt. It's going to turn from a solid into a liquid. So this is a state change, which would be a physical change. If you grill a steak, what type of changes are occurring? Here we're going to be heating up the steak. The heat is going to cause chemical changes to occur because different molecules within the steak are going to undergo reactions and turn into different molecules. When an apple sits out on the counter and turns yellow, what type of change is occurring? This example is actually kind of tricky. At first we might think this is a physical change because there's a change in color, and color is a physical property. But in this example, we're actually seeing a chemical change. The iron that's found in the apple is actually rusting as the apple turns more and more yellow. This is a change from iron going from iron to iron oxide and would be a chemical change. The final example, when a mango falls from a tree and begins to rot, what type of change is occurring, is also an example of a chemical change. The molecules within that mango are being broken down into more simple molecules. This would be an example of a chemical change.